Hello, everybody. I'm Jean-Christophe Ehrström from Constellium, and my co-authors are Julien Laye, Ehrström Nizery, and Nicolas Bayona from the Histoire plant of Constellium. The title of the presentation is Damage Tolerance of a Hybrid Lowering Molded Stiffened Panel with a Fiber Metal Laminate Skin. And fiber metal laminate is a proposition that we make to have a very high damage tolerance low wing associated with an improvement of the overall wing concept with advanced alloys of the aluminum copper lithium family, airware family, and associated with bonding and also friction stir welding. Fiber metal laminate skin is a way to have a robust weight saving, whatever the assumptions regarding the inspection intervals or the design service goal, more or less. Fiber metal laminates are well known. They are known under the trade name Glare, and they are flying, those materials are flying on the fuselage of a A380. So it's a real industrial material. However, on the fuselage, the metal sheet of the fiber metal laminate are thinner than what we are going to test here in the present panel test. Fiber metal laminate is a combination of fiber reinforced epoxy, glass fiber reinforced epoxy layers, and thin metal sheet. It's certified as a metal, so not as a composite, even if it's in effect a composite material. It has the attributes of metal like ductility, oxidation, fatigue sensitivity. It can be machined, and the composite aspects are limited to the drill holes. It has, very importantly, it has electrical conductivity. The basic principle of the fiber metal laminates, why they are very good in fatigue crack growth, it's because the loads or the stresses from in the metal sheet are transferred to by crack bridging to the composite made of epoxy, matrix, and fiber and glass fibers. Now we come to the objective of the test that we have performed. In fact, for making a lower wing, we want, for cost reasons, to have a thicker metal sheet compared to what we have in the fuselage. So it makes sense to make a test that would validate this increase in the thickness. But still, we want to have the attributes of the FML, that is a very large inspection interval possible. So we target factor 3 versus a current inspection interval. And also we want to target a very high design service goal, that is fatigue life of the panel. And you can see here the panel, it's made of FML with a 2024 sheet and 2027 stringers that are bonded onto the skin. We have put an initial defect that is very conservative. It's over a rivet hole. We have water cut 3.5 millimeter notches on each side, and it makes a 15 millimeter defect. A typical defect would be from a hole would be a 1.27 millimeter rock flow. So here we are really very conservative in terms of starter notch. For performing the test, we have used a thermo-elastic stress analysis in addition to visual inspection. So this requires this black area where the analysis of thermal variations is monitored. And you see the rivets, and you see as well the strain gauges that are used to be sure of the loads that we are applying. And with a visual inspection periodically, we have monitored the crack growth in the panel. You see here the panel from the back, and the stringers are on the opposite side. There was an initial question about what would be the appropriate loading of the panel. We selected the constant amplitude loading at 135 MPa maximum stress. That is representing a 1G stress of 90 megapascal. This is a factor of 1.5 between the 1G stress and the constant amplitude stress. One cycle at R equals 0.1 represents one flight with a 1G stress of 90 megapascal. This is typical from the literature. It is also consistent with what you see on the bottom left, the typical twist spectrum. You see that it's, in fact, the 1.5 is also a factor um, that represents the maximum stress in a flight for most of the flights. In the paper, we are going to further validate this assumption based on the literature, but it's a common assumption. So the 90 megapascal 1G stress is a relatively high stress, and that's what we want because we want an improvement versus a typical stress for a bulk material. For 2024 in the literature, we see 75 megapascal as a typical allowable fatigue stress or fatigue crack growth stress. It's rather on the high end of what is assumed for 2024 bulk material. So here we have a 20% improvement of allowable stress. This is the overall result of the test. You see that we have started with the blue defect position with the blue arrows, initial defect, the 15 millimeter altogether defect, and then the crack grew to orange position, where we have the first detectable event of 39 millimeter long crack. It is often assumed that a 1.5 inch crack is visually detectable. But then we continued the test to a second detection event, which is the top flange of the stringer is broken. That is in green. The crack position is shown with the green arrows. And then we further grew the crack to the first position of the red arrows for a first residual strength test, which didn't lead to any crack growth. And we further loaded the panel up to the second arrow positions, where we made a second residual strength test. The residual strength test has to be such that the limit load is sustained, and the limit load is by definition 2.5 multiplied by 1G stress. So it should be at least 225 megapascal. Here we had a machine limitation, so that was at 257 megapascal, so it's over the 225 megapascal. So we managed to largely reach the limit stress that was required. So altogether, we can say that we have tested the pattern with the representation of a 90 megapascal 1G stress, even if it was in reality R equal 0.1 with 135 megapascal maximum stress. And with that, we had 135,000 flight cycles between the last detection event, so the most conservative assumption regarding detection event, and the residual strength test, so that with a factor 3 on the number of cycles, we can guarantee a 45,000 flight cycles inspection interval, which is largely above what we have in current aircraft, which would be typically 15,000 cycles. With this 20% increment in 1G stress, that is 90 megapascal versus 75 for bulk 2020-43, we have we have an improvement of weight that is possible with of 20%. But in addition, we have the density effect. It's about 7%, so we are talking about 25% weight saving potential for this panel. Here it's a detailed view on what happened on both crack tips, the right-hand side and the left-hand side. You see that the crack growth is relatively linear, like in FMLs, and not accelerating a lot. There is a jump at a certain point on the black line. This is where the crack is crossing a rivet and finishing the fracture of stringer. And that was just before the first residual strength test. Then there is a question whether by improving the allowable stress, fatigue allowable stress by 20%, we would reach other design criteria associated with, for instance, shear loads coming from elastic response and so on. In fact, we have presented in 2017 the result of a full wing model with aeroelastic loads, and including all the design criteria on static performance, the multi-axial yielding envelope, the knot strength, the splicing. And in fact, we had very consistent results with what we have just shown, because we could improve the fatigue crack growth allowable by 20% and have a factor 3 in inspection interval without reaching the other criteria. So in conclusion, we have validated this improved concept of FML for allowing, that is improved by reducing the cost thanks to thicker sheet, 0.8 rather than 0.3 or 0.4 millimeter for fuselage. The stringers were bonded and behaved well. The residual strength is very high. It was over the 225 required, but limited by the machine to 257 megapascal, and this is consistent with the 1G stress of 90 megapascal. The 1G stress of 90 megapascal was represented in fatigue by a constant amplitude loading of 135 megapascal. And with that, we could reach 135,000 cycles between the last detection event, a broken stringer, and the residual strength test, allowing a factor 3 on the inspection interval versus current normal numbers. So in the end, we validate a 20% increase in stress allowable in fatigue crack growth, but that is consistent with other criteria as well. And with the 7% density reduction, we are talking about 25% weight improvement versus a current 2024 T3 bulk wing skin. Thank you for your attention.